Well, hello there, and welcome back for more Advent of Code 2022 in 2023. So yeah, the year has gone by, and I still haven't finished the Advent of Code puzzles, but I still want to give it a go. So let's see what's the next puzzle about. So day 15, beacon exclusion zone, and this is beacon, not to be confused with bacon, which I always do, and I feel it's usually more fun to read it as bacon. But let's see what this is about. You feel the ground rumble again as the distress signal leads you to a large network of subterranean tunnels. You don't have time to search them all, but you don't need to. Your pack contains a set of deployable sensors that you imagine were originally built to locate lost elves. So yeah, we were following a distress signal and we got into a tunnel under a waterfall, if I remember correctly. Okay. The sensors aren't very powerful, but that's okay. Your handheld device indicates that you're close enough to the source of the distress signal to use them. You pull the emergency sensor system out of your pack, hit the big button on top, and the sensors zoom off down the tunnels. Wow. This seems very high-tech stuff. At least like compared to the handheld device that you're carrying that has a CRT tube, or I guess a CRT display. So okay. Once the sensor finds a spot it thinks will give it a good reading, like yeah, these things are super intelligent, it seems like. The sensors think. It thinks it will give it a good reading. It attaches itself to a hard surface and begins monitoring for the nearest signal source beacon. Nearest signal source beacon. Okay. Sensors and beacons always exist at integer coordinates. Okay, thanks. Each sensor knows its position and can determine the position of a beacon precisely. Good. However, sensors can only lock onto the one beacon closest to the sensor as measured by the Manhattan distance. Okay, so this is a link to the Manhattan distance Wikipedia, which I think is also known as like a taxi cab distance. So this is basically, instead of taking the square root, for instance here from this point to this, and this is 1, instead of being the square root of 2, this is 2 because you need to move in a square grid. So okay, there is never a tie where two beacons are at the same distance to a sensor. Oh, this is good. So okay, the sensors then locate the position of the closest beacon. Okay, this is giving me some flashbacks of a puzzle from last year's Advent of Code, or I mean last year's 2021, which was about also like sensors that were like positioned in 3D space, and they could be rotated all the way around, and it was a difficult puzzle, that one. I hope that this one isn't as difficult. Okay, at least it's 2D, it seems. It doesn't take long for the sensors to report back their positions and closest beacons, your puzzle input. For example, sensor at 218, closest beacon is at -2 and 15. Okay, I wonder if these coordinates for the beacon are like relative to the coordinates of the sensor. We're probably gonna get that sorted out. So consider the sensor at 218, the closest beacon to it is at -215. For the sensor at 916, then the next one, closest beacon to it is at 1016. Okay. Drawing sensors as S and beacons as B, the above arrangement of sensors and beacons looks like this. Okay, it's also interesting that there are like negative numbers for these coordinates. Okay, so let's check, for instance, this sensor at 218. This would be here, row 2, and 9, 18, so I guess it's this sensor, and there's a beacon at -2, 15. So it's this one. Okay, so the positions of the sensor, of the beacons are not relative, I think, to the sensors. They are like absolute positions, so that's nice. This isn't necessarily a comprehensive map of all the beacons in the area, though, because each sensor only indicates its closest beacon. If a sensor detects a beacon, you know there are no other beacons that close or closer to the sensor. There could still be beacons that just happen to not be the closest to the beacon to any sensor, the closest beacon to any sensor. Okay, consider the sensor at 8.7. Okay, so this thing at 8.7, the position of its beacon, let's check it here, I guess. 8.7, this one. The beacon is at 2.10. So, okay, yes, it's this beacon. And so you know that there are no other beacons in this area. So this is the area using the Manhattan distance that creates this kind of like rhomboids. I don't know. I don't remember the rhombuses. Okay, this sensor's closest beacon is at 210, and so you know there are no beacons that close or closer, and any positions marked as a hash sign. Okay, yeah, good. None of the detected beacons seem to be producing the distress signal. Okay, so you need to work out where the distress beacon is by working where it isn't. Wow, okay. For now, keep things simple by counting the positions where a beacon cannot possibly be at just a single row. Okay, this seems like it's going to get complicated in part 2. So suppose you have an arrangement of beacons and sensors like in the example above, and just in the row where y equals 10, you'd like to count the number of positions a beacon cannot possibly exist. The coverage from all the sensors near that row looks like this. Okay, so this would be like painting all of the sensors coverage. In this example, in the row where y equals 10, there are 26 positions where a beacon cannot be present. Okay, consult the report from the sensors you just deployed in the row where y equals what? 2 million? How many positions cannot contain a beacon? Okay, we jumped from 10 in the example to 2 million. And let's see the input. Okay, so at least the input is not huge. Like, it's not like there are that many sensors. But yeah, all the positions are like in the order of millions. It seems like near 4 million here. And are there any negative positions? Yeah, there are a couple of negative positions too, of minus 4 million almost. No, this is not 4 million. This is, oh, it's not even 1 million. That's good. Okay, so the negative numbers are not so great. Interesting. Oh, and there are some beacons at y equals 2 million. This, I guess, would be important because here in the example there is also a beacon here. So, okay, and for this example, the answer is 26 positions where the beacon cannot be present, which I guess should exclude this beacon. I don't know if it includes or it excludes this beacon that is already being picked up by the sensors. So let's count. This is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, it's difficult to count in my non-native language, but I think I counted 26 without counting this beacon. Okay, so we have to not count these things. And we have to manage very large sizes of this grid. Interesting. So I guess the challenge here will be to, handling these large numbers, not because they are too large like for computers to handle, of course, but because like they are in the order of 2 million or like 4 million. And if we go for a very naive solution of like modeling the grid as a 2D, like a flat 2D array, or like vector of vectors, we're gonna run out of memory, because like imagine 2 million is like 2 megabytes if you use only one byte for each tile or for each position. But then if you're going to have like 2 megabytes times 2 megabytes, that's 4 terabytes, and that's more than the memory that I have. It's even more than the internal disk space that I have. So definitely wouldn't fit into memory having a flat grid for everything. But fortunately, we only need to consider this line at y equals 2 million. So I guess we could try to go for a naive solution of only considering that line and counting like all the, I don't know, going from -1 million to positive 5 million or something, count all the positions there and ask, if any of those positions is near a beacon and should be like excluded or not, to give the part 1 answer. Yeah, I guess that could be a reasonable approach for the part 1 answer, without like optimizing too much, and to see what the part 2 is about. So let's jump into it. Let's jump into Advent of Code 2022 and fire the text editor. Let's close everything besides main and create a new input file. This would be day 15 txt. It's a notification here. What is this about? Yeah, Rust analyzer. Reload if you want to. Okay, and we are gonna use the sample inputs first. Yes, and let's also create a new file for this, a new module, I guess. What was the name of this? Beacon something? Beacon exclusion zone. Okay. Exclusion zone. Okay. Let's use it here. And let's create a file for the solution. Beacon exclusion zone .rs. Okay, and as usual, let's have the public function run that takes an input string and returns a string, then have it into a known string and reload the file as usual. And okay, how are we going to do this? First, we need to parse this input, which I guess we could try to parse as Sorry, I got an almost sneeze that doesn't want to come out, so I might get a sneeze anytime soon. Trigger warning for headphone users. So okay, how do we parse this? I guess we could try to see if we have any numbers in one line. Yeah, we could do a very dirty parsing of like reading each line and splitting by equal sign or by commas or by colons, and that's it. And then getting all those parts and parsing the ones that are numbers. I think that could probably work. So, okay, and I guess we're also going to need a structure to parse these things into. So let's call it struct sensor. So we're gonna have position, which can be a point, and a beacon position, which should be also a point, and let's have a type point that can just be a tuple of numbers. I guess we can use 32-bit numbers for this, because these numbers are not so huge, and they have to be signed because some of the positions are negative. Okay, so let's see, let's have sensors parse sensors and pass the input. Yeah. Okay, and here we just return a vector of sensor, and we are gonna do input lines. Yeah, map, and we can also extract this further and say parse a single sensor. So parse sensor and collect into a vector. So for this we have a similar function that will do. I guess we could have a single line, type string, and return a sensor. And what will we do here? I guess we can have this line and split it by what was it? Either equal sign, or I think commas, yes, or commas, or columns. So this, and I think we can pass it like so, and then we are going to have this all of these things, and what are we going to do? We can try to parse all of these parts of the line into a number, and the things that are actually numbers, we can, so let's say we can collect them. So let's say let numbers be this and map it to, so each part we're gonna do parse, and so this would be a vector of 32s. We're gonna try to parse, and I guess we can say filter map, so to filter out the things that are not actually numbers. So this doesn't work. Let's see why. Yeah, expected a sensor. Fine, we can try to return a sensor here, and filter map. Of course, we need to collect here. Okay, and then okay, so filter map expects an option, but it found the result. I think we can convert to convert a self into an option. Yes, I think this is what I want. So we'll have numbers as a vector, and we can do something like let's destructure these things. So numbers, numbers, let's slice it all, and say, so first we are going to have the position I think, the XY coordinates of a sensor. So this would be, let's say, SX, SY, and then the beacon X and beacon Y. And so we should have these 4 numbers, but if there aren't 4 numbers in the line, we're gonna panic and say invalid line should have 4 numbers. And we can put the line in here. Okay, and finally we can have the sensor position be SX and SY, and the beacon position be BX and BY. Good. Very, very nice. And let's see if we parse this correctly. Let's derive debug here and do a println of these things. Okay, and let's do a pretty print, I guess, of sensors. I wonder if it would be better to return 2 different, instead of returning an array of sensors here, just return 2 vectors of the sensor's position and the beacon's position. Maybe that will be better, but I don't know. Okay, let's run. Cargo run day 15. Okay, so we parsed something successfully. Let's see if this makes sense. So 218 and minus 215. This looks fine. So okay, it seems like this hacky way of parsing worked, and that's very nice. So this is the sample solution, and we want to see what happens at line 10. Okay, so let's go for a very naive solution and see if we can get it working. So what are we going to do? We are going to iterate the x coordinates. So let's say from some minimum value, we could say something like let's min x be well, let's actually hard code these things for now. Like I just want to get to an answer. So yeah, let's say min x, just hard code it to, let's make it work also for the actual input, which is much larger. So minus 1 million to max x be, I think the actual input has like numbers in the range of like 5 million or at least 4 million. Yeah, here we have something bigger than 4 million. Okay, I don't know. Let's go to 10 million just to be safe. This might take some time to compute, but I mean, computers are fast, so maybe this is good. So what are we going to do? We're gonna go for x in this range, min x to max x. And so we basically want to know if we are close to that beacon or not. To any beacon, actually. So we'll probably express this in terms of iterators. So let's say I don't know how to call this thing. So or excluded positions count, which would be the answer to part 1. It's going to be this thing. We are going to filter out anything that is so anything that is close enough to a sensor, and then count, I guess. I don't know if I should use count or length here. Isn't there a length method? No, so I guess count should be. And what's the predicate? So okay, we're gonna filter the axis that's I guess we need like the distance of that sensor to the beacon, to its beacon, and we're going to compare that to the distance of this x coordinate, and the, I guess we can say, let's y be, for now it's going to be 10 because this is the sample input. So from this xy to that sensor, and we are going to compare those two distances. And you know, if we are less than that distance, from the distance from the sensor to the beacon, then we should be excluded, I think. So I guess we can compute that distance right away when we are parsing. Otherwise, we are going to be computing the distance. Well, let's actually keep it in another array. We can do that. Beacon distances. Oh, but then I would have to ask using. Sorry, what am I trying to do here? Yeah, we could I guess have the distance here. Beacon distance, and this should be. And I guess you can also use an I32. Why not? So the beacon is gonna be. How do we do the distance? The Manhattan distance. So we can have Sx minus Bx and take the absolute value plus the difference between Sy minus By, and again take the absolute value. So it's basically the. I think this is correct, right? So if we have, for instance, let's do some ASCII drawing here. Well, let's go and draw the full thing. So this is the center. This should be a sensor. So this point here would be at the x distance would be 1, and the y distance. So okay, this would be a distance 1. This will also be a distance 1. Sorry, this would be a distance 2, and this would be the difference in x position plus the difference in y position. So, and the absolute values of those, that would be distance 1 and 1. So this is also distance 2, and this is also distance 2. Okay, I think this sort of makes sense. So this is the beacon distance. And okay, and here we need to. What are you complaining about here? Expected comma. Okay, have the comma. We can say let distance be, well, I guess same thing, but to the vector. So we can say, oh, actually we need to iterate. Yeah, we need to iterate over all the sensors here. So sensors. So if there is any sensor or some sensor, yes, whose position is closer to us than its beacon distance, then we should be excluded. Yes. So we can say the distance to sensor. Let's call it just distance, and this is a sensor gonna be, I guess we have to do the same thing. We could actually extract this thing. Let's be good boys and have a function for this. We could call this thing distance. And we could actually receive 2 points, right? And say x1, let's call it the same way, sx and sy, this would be a point, and then have bx and by, this should also be a point. Okay, then rename these things to be x1 and y1, and to be generic, x2 and y2, and here we're going to pass these tuples. Okay, all right, and here we're going to need the distance between the sensor position and xy, and then say if this distance is less than sensor beacon distance. I don't know why I'm not having, I'm not having autocomplete because this sum is for iterators, I guess. No method sum. Is there a method any? Yes, there is. Okay. This is a reference. We can dereference this. Guess we can do it here. And let's print this thing. So formats. Okay, this seems suspiciously simple code. It's taking its sweet time because it's doing like 10 million iterations. I guess I could reduce the size. 64. That's not what I wanted. It was something like 23 or something. 26. Okay, so that's not good, but at least it's not in the millions, so we didn't do it that bad, I guess. So what did we do? Does this look sensible? It does. x1 and y1, x2 and y2, so oh, here I am passing bx. So this is sensor x and sensor y, and this should be, actually this is a very stupid mistake. This should be beacon x and beacon y. Let's use less humongous numbers for now. Okay, let's run it like this. And 23. No, sorry, but 23, but I wanted 26. So what went on there? I'm doing, am I having like a off by 1 error? Maybe that's the case. So yeah, I think we should be excluded if the distance is less than or equal to this thing. So let's see now. 27, and now we are off by 1 in the positive direction, but I think we should also not count the beacons that are in this position, in this y coordinate. So let's do that. I guess we can subtract from here, or we can do it if there's any sensor there, okay. And we could, let's say we have this, and let's do excluded blah blah blah. subtract the beacons positions that are at that line 10. So sensors, iterator, and filter the ones that's we're gonna have a sensor. Well, let's actually distract this maybe. Sensor. Wow, no, just call it sensor. Okay, and the sensor beacon position x, which should be the first coordinate of that tuple, is equal. No, sorry, it should be y is equal to our y, and count this up. Okay. So if we run now, we have 20. What? 24? Why? Like if we print line this thing before, it was 27, but are there, like, in this drawing we have only one beacon at this line 10. Are there x equals 10 there? Oh, okay, there are 3 at y equal 10. Why are we only seeing one here? So, okay. To count the number of positions a beacon cannot possibly exist. The coverage from all sensors near that row looks like this. So why do we have this beacon here? This one is this, I think, at 210. So yeah, this one is at 210. We are also covering by other stuff. Wait, shouldn't be there more beacons here in line 10? What am I missing? Closest beacon is at this one at 210. Oh, okay. there are many beacons at 210. I didn't realize that the X position was the same. So many sensors are detecting the same beacon. That's interesting. That's interesting. So we have to not double count, I guess. Okay, so how do we? I think doing this here doesn't make much sense. We try to see it here. So if we are close to this, like if we are in this sensor's exclusion zone, we have to not count if we are at the same position of the beacon, right? Yeah, I think so. So we can say, let's call it in sensor exclusion zone. So let's say that we are in the sensor exclusion zone and we are not in the beacon position. So sensor beacon position is different to xy, I guess, or not equal. So right, and then we should need to do this, and this doesn't need to be mutable. I don't know if that logic makes sense, but let's try it. Yes, 26. Okay, very good. Let's try this thing with the actual input. removing this print line and copying this thing, pasting here, and changing this to line 2 million. Let's go then over the millions and let's cargo run, but in release mode, so it doesn't take that long. It's okay, that didn't take that long, and the answer is 5 million and something. Well, I don't know if that's the correct answer. Let's try it actually. That's what that stupid code says. Yes, it is the right answer. Nice. But I bet, I really bet you that the part 2 is gonna invalidate this approach, I think. Okay, part 2. Your handheld device indicates that the distress signal is coming from a beacon nearby. The distress beacon is not detected by any sensor, but the distress beacon must have X and Y coordinates each lower than 0, no longer than 0, and no larger than 4 million. To isolate the distress beacon's signal, you need to determine its tuning frequency, which can be found by multiplying its X coordinate by 4 million and then adding its Y coordinates. Okay. In the example above, the search space is smaller. Instead, the X and Y coordinates can each be at most 20. With this reduced search area, there is only a single position that could have a beacon, X14 and Y11. The tuning frequency of this distress beacon is this thing. Find the only possible position for the distress beacon. What is its tuning frequency? Okay. So 4 million. The naive solution for like iterating X and Y from 0 to 4 million doesn't seem like I'm checking, you know, the only position that that is not excluded. Doesn't seem like a reasonable approach. So what could we instead do? Like a reasonable approach, I mean, in terms of time, is gonna take way too long, I think. We're talking about, like, in terms of memory, I cannot represent this in a 2D grid and exclude everything. And in terms of time, I guess, you know, the computer is like some gigahertz of frequency in its processor, so it can process like billions, also known as thousands of millions of operations a second. But still, we are talking about terahertz needed to do this in like 1 second or in seconds. So we are talking about, like, in terms of gigahertz, like in terms of around the ballpark of thousands of seconds, and I don't want to wait so much. So this is a very like brute force approach for part 1, and I think like at least for one line like we are doing here, I can think of a simpler approach. Like if we let's try to do some ASCII drawing again. Let's say we have a beacon here, or sorry, a sensor with an exclusion distance of 3. So we have something like this. Okay, probably don't need to draw all these many lines, but I mean, let's consider these things line 0, 1, and 2. We can write those. And let's see. If we are, for instance, in line 2, we don't have to iterate over each position to count how many positions are excluded by this sensor. We can do, okay, the distance from line 2 to line 3, where this is 1, and well, the seeing, like the beacon distance of this sensor is 3, so we can do 3 minus 1, that is 2. So we can, I think, take the x position of the sensor and do minus 2 and plus 2 to have the range of that sensor in this particular line, line 2, or I have to connect my notebook. Okay, we are powered on now. Okay, so yeah, we could do a direct calculation, and then we know where this exclusion zone line starts, or sorry, where the exclusion zone overlaps with this line in particular. So here it would go from 0, 1 to this coordinate, and we can do this minus this and get the whole line. But then we have the problem of like overlapping sensors in here, so we don't have to like double count. So we probably need to do some intersection of line segments. That doesn't sound like that complicated, but that's only for one dimension. We need to do something similar for the 2 dimensions for the part 2 answers. And I'm not sure how to do that. So let's maybe let's plot the input grid. So the sample input grid. And so the answer, the only position is x14 and y11, where we are not excluding any, that is like not excluded by any sensor. Maybe we can get an idea of that then. Okay, so let's go and say, yeah, from let's say minus, I don't know, 10 to, like, because here we are asked for the sample, it would be, sorry, on part 2 we are interested at most 20. So let's go set 10 more to each side, and let's say let's y in or I guess x in minus 10 to 30, and let's y go also from minus 10 to 30. Let's also have a set of variables like this, but repeated for the sample input. So we can go from, I guess I can use those same numbers. 30, and the line is at 10. Let's see if we still have the same answer for the sample input, which was 26, I think. Yes. Sure. Oops. We go from main x to max x inclusive. Well, let's do it all hard-coded. And what do we need to do here? So So I guess we can do something like have a grid, right? Sorry, I'm having some problems thinking of what I want to draw here. So let's see. We're going to do this. Let output be a string. So something like this. And here we're going to just push a single new line as usual, or just actually println a single line, and we are going to compute that line by doing something with these coordinates. Let line be this thing. We're actually going to do something. Well, no, actually, let's do map to a single character, and then we're gonna collect into a string. And here we're gonna have the this is sorry, what is this? It should be y, and this should be x. Okay. What are we going to map to? So I guess if there's any sensor in this xy position and you want to draw an S, so if sensors any, no, sorry, iter any S position is at xy, then we're gonna return S here. If there's any sensor, like similarly, if there's any beacon in this position, beacon position, we're gonna return B, and otherwise, if this should be excluded, so this calculation, so well, actually we can do something like this. Oops. So we can call this let's excluded that yeah, something like this. So if excluded, then we are gonna return like we are going to draw a hash, or else just draw a dots. And do you like this thing? Why don't you? Oh, I guess we are shadowing this variable or something. No, this is not let, this is a for loop. Okay, now it likes the syntax, and let's run with the sample input and take a look. Oh, look at this. This is very pretty. And I guess this is the only dot that is not excluded in this. Okay, yes, we can go then. If we replace this from 0 to 20, I guess I bet that if we draw the same thing, yeah, we're only going to have a single dot here. So that is our answer for the sample input, but we cannot do the same thing for the actual input because it's going to take freaking long time. I guess I could program it and build it in release mode and let it running for, I don't know how much time is 1,000. I guess it's less than an hour. Maybe it's going to take less than an hour. Like I'm not sure, but it's going to take like several seconds, in the order of thousands, I think. So I think it would be nice to think of a better approach here. So okay, for a single line, I can think of these things. But for the actual 2D grid, how do we approach this? Well, we could actually think about something like the single line approach. Like, if we know how to do it for a single line, this overlapping of segments, then I guess we could brute force that approach of a single line, scanning through the 4 million values of all the rows, for instance, for 4 million rows. And whenever we find that the excluded count of positions is like one less than 1 million, sorry, that 4 million, I guess we know that the answer is on that row. Something like that could work probably. Yeah. I do wonder though. So, okay, I think I do have an idea. I don't have much time because I have a meeting to attend to at 6 p.m., also known as 18. So, let's try to. We don't need that drawing, I think. And let's actually comment it just in case. And okay, let's do something. Let's try to improve the part 1 solution, trying to do this more clever thing about thinking of all the like sensor segments in this line, and then joining them all up together to avoid any like duplicates, and then try to get the same answer for part 1 and check that it actually runs faster, and then try to brute force the answer for part 2 using that same approach. Okay, so let's do this again. So we're going to do run release, and let's time it. Time target release output of code blah blah. Oh no, sorry. This shouldn't be run. This should be build release and run day 15 with these huge numbers. It does take something like 600 milliseconds on like this naive approach. Okay, milliseconds, interesting, for a whole line. So if we want to like half a second, let's round it to that. So if we want to make this same approach for the 4 million rows that we have to check, well, actually doing this for let's go from 0 to 4 million. and count this. This won't give us the right answer, but we can have an idea of how much it takes to do a single row. Okay, so a quarter of a second. So if we do this, well, times 4 is a second. So for the 4 million rows, it would take so 1 million seconds, right? Sorry, I was thinking that it was in the order of thousands of seconds, but it's actually going to be 1 million seconds, which is a huge lot, right? If we do, I don't know how to calculate in my head. So this is 1 million divided by seconds divided by 60 to get minutes. Let's do it in floats. And then divided by 24 to see the hours. No, okay, this is way too many hours. Yeah, it was way off when thinking about brute forcing this. This is going to take like a stupidly big amount of time, so it's impossible to really brute force this naive of an approach. So, okay, that's fine. We could also think of min x and min y in terms of trying to get the minimum and maximum coordinates of these sensors, but I don't care about that. Like these rough numbers are okay, I think, for me, because for a more clever solution, I shouldn't be hard coding this min x and max x. Okay, so let's do something like cargo run release. So this is the actual answer, right? Oh, 0. Why? What did I mess up? We are printing this. Oh, but we have the sample input. So let's put this again. And we have this 5 million thingy that we have submitted and is correct. And let's actually get rid of this code. I want to just have one work in progress or tentative commit, naive day 15 part 1 solution. Okay, and I think I'm going to pause the video right now and go attend this meeting, and then I will be back. Okay, so this will be a pause. No, let's actually end the recording right now, and if this can be a single video, I guess. So if you have been, thanks for watching, and see you again in part 2. Bye bye.